Hello, my name is Michael Bausch, and today I'm going to be talking about the Fermat-Torricelli problem and different sort of various solutions that it has. And so, a great place to start with this is, what is the problem? So, to define the Fermat-Torricelli problem, I'm going to use this formula. Basically, given points ai as an element of R of n, as I equals 1 to integers to n, define the non-smooth convex function sigma m I equals 1 and then x minus ai, the sort of length. And so your solution that you're looking for is to minimize phi of x over all x as an element of Rn. This is quite a bit of math, and so to portray it visually, we can say that you're trying to find some point S that makes the distance between it and all others minimized, this being sort of these yellow lines, and then you can just pick any sort of S, add up all the sort of distance between them, and then you want to find the minimum distance for that. And I will be referring to S as the minimum distance point of all of these functions. So this definition sort of mentions the fact that it is a non-smooth convex function. And we sort of, or going into this, I should say, I sort of had a concept of what a convex function is, where, you have smile up is convex, smile down is concave, that sort of thing. But what I didn't know is that sets can also be convex, which is pretty cool. But the Fermat-Torricelli problem describes points that make up this convex sort of set. And mathematically, for f of x, we have this sort of function, f delta a plus 1 minus delta b is less than or equal to delta f of a, for a, b, and delta are elements of all real numbers. And so this is, once again, just sort of like a big sort of formula to illustrate this sort of point, which is like all possible line segments between any 2 points in this shape should connect if it's convex. They should never go outside of this set. So, for example, this shape is convex because any sort of 2 points, any sort of line segments that you have within this will all be connected. And then this is not, because you can take 2 points and then have the line segments connecting them sort of not be in that set. It's sort of like a self-contained sort of set. But this mathematical definition is going to be useful later because, or I shouldn't say later, I should say now, because the Fermat-Torricelli problem is convex. We will know that it has one unique solution. And so the proof, which is from my source right here, is very complex. It deals with subdifferential calculus, which is obviously not within the scope of what I kind of want to talk about, but you can take this sort of function, plug in the original problem that we had sort of with this phi, and then you can kind of do a bunch of math on it and then get this out, where essentially what you would get would have a contradiction if there was more than one unique solution. So this is important because it sort of sets the groundwork, which is that we're looking for, regardless of dimension, we're looking for one point that will be our minimum distance point. So the general solution is something called the Weisfeld algorithm, and I'm going to set the stage for this a little bit because my colleague Cyrus will be later talking about how to solve this with Excel, which is super neat, but obviously I'm not looking into that. This sort of function is sigma notation m I equals 1, x minus ai over sort of distance of x minus ai, for x is not an element of any of these a1, a2, am points in Rn. And so solving for phi of x equals 0, we sort of can get this function, which works for all Rn with any number of points with a couple conditionals. But this function is a recursive algorithm where essentially you can plug in any sort of value for x, and then it will sort of output something closer to your function. So you can keep putting that output back into it over and over again, and then it'll move closer and closer to the solution. And that'll kind of be how you solve this. Yeah, so my two conditionals on this are, one, this is a recursive algorithm, like I said. So if it runs into any of the points, it will essentially break, because this x minus AI, if the AI is any of these points, which is mentioned sort of in my definitional, if it runs into any of those points along the way, you're dividing by 0, and then it won't know what to do. And also, the points can't be collinear, which essentially means they can't be in a line. And this is just because then you sort of, it technically is defined as a convex shape, but it's sort of got other stuff going on. But because it is within the scope of the problem, that means that we can indeed find a unique solution for it by the proof. So this is going to be our first out of 3 examples, or 3-ish examples of solutions to this problem that are bound by things. I'm going to call this our sort of dimension 1 solution, our R1 solution, because, you know, it's a line, so it exists in the first dimension. But if we have a line, we can sort of solve this with very basic algebra. Because, looking at our problem, we want to take the distance from our minimum distance point of all these points and then kind of add them up. So, for example, in this one, if we take a random point x, let's make x, which is not the minimum distance point, but let's make it between a2 and a3 and just do some very simple algebra. You know that because some of these are to the left of it and some of it is to the right of it, some of these will have x minus ai, and then the other ones will have ai minus x. So because this is between a2 and a3, this means x minus a1 plus x minus a2 plus a3 minus x, etc., will be your sort of setup point. And so if you do some basic algebra, you realize that sort of these x cancel out. And because we have an odd number of x's, you end up with negative a1 minus a2 plus a3 plus a4 plus a5 minus x. And this sort of function, if you want to minimize x between a2 and a3, you sort of realize that to cancel it out like minimally, you want to be closer to a3. And if you perform this sort of function on like every midpoint, you'll realize that it's always trying to get you to move closer to a3, which is the median. So the solution for these kinds of collinear problems are just literally the median. And if there is no median because you have an even number of points, the answer will be anywhere in between your sort of 2 middle points. For example, if you only had, I almost put my thumb over the screen to cover up, but if you didn't have this a5 here, and it would just be anywhere between a2 and a3, which is pretty cool. It's a pretty sort of simple solution. And so what about other constraints? So let's look in R2 with 3 points, because that's just pretty simple triangles. So if no angle is greater than 120 on this sort of triangle that is formed by these 3 points, you can solve this with pretty simple and interesting geometry. Essentially, you can take any 2 points, like a1 and a2, and you can take this and build an equilateral triangle off of it. And then you can do this with sort of the opposite sort of points, and then draw these lines between like f and a3 here and d and a2, and then by doing this, you will find the intersection is your minimum distance point. And this sort of makes sense logically if you're just thinking about how, you know, it's sort of like symmetrical, it's got this sort of symmetry, so you would expect it to be on that sort of, like, maintain that sort of symmetry property. And so this is a pretty easy way to find the minimum distance point. It doesn't require any sort of fancy algebra. You just can, you know, draw it out and then find the solution. And so if any angle is greater than or equal to 120, the minimum distance point is not constructed like that. It is simply just the vertex. For example, here it would be a3. So this also sort of, at least for me, it sort of logically makes sense where, you know, you have these 2 points are like pretty far away, and then it's got stuff to do with angles. But both of these also come from a different theorem, which is also sort of out of the scope of what I wanted to talk about, but it essentially comes with using cosines on the Fermat-Torricelli problem and then sort of like plugging it in and getting some more sort of cosine stuff out, which you know, I just wanted to put this here to prove that, you know, there is math behind it that works with the actual problem. But at this point, you may have realized, you may not have realized, and I didn't realize, which made it really interesting when I was looking at it. But there's sort of this important rule of symmetry that has to do with all of our examples so far, which is, we've had the point be the median, which is sort of the median, sort of not exactly midpoint, but it's kind of in the middle. And then we've had the triangles, which sort of have this symmetry line of it. And if you have these 2 points that are sort of equidistant from each other, you know that this sort of has to be on this line of symmetry, at least logically. This is just because, if you're looking for something that's equal, not necessarily equal distance, but minimum distance, and then you have 2 points that are equal away from each other in such a way like this, it only makes sense that if you wanted to get the minimum distance, you would want it to be on this line. And so we can use this sort of rule to find the minimum distance in shapes with lots of symmetries. For example, 4 points forming a square in R2 in the second dimension. So, like, for example, you have this sort of like square that I've drawn here, and if you look at the reflectional symmetries of a square, there is a lot of them. There's a really interesting lab that you can take here on symmetries if you're interested. But because there's so many symmetries, because like if we were looking at our last rule, we sort of knew that it had to be on this line of symmetry, like logically, the minimum distance point should be at the intersection of all of these reflections. And so because we can kind of piece that together logically, we know that the minimum distance point has to be exactly in the middle of this square. And it doesn't matter if it's a unit square or if it's a larger square, we just know that the midpoint is also, or the minimum distance point is also the midpoint, which also happens to be the average of all 4 points, which is just pretty nifty. So that's just sort of 3 sort of bounds that I wanted to talk about for this problem, working off of, I'm not going to go any higher than the second dimension, simply because after that point it gets more into this sort of very difficult math. But I wanted to talk about these 3 problems in particular. Sorry, I'm scrolling back up to this algorithm. It sort of has to do more with this kind of stuff. But I wanted to talk about this because I just thought it was really interesting that this problem, which is, it seems like it would have a simple solution if you're just reading it. And I expected it to, and then I saw this and I got kind of intimidated by the concept of like recursive algorithms and like using computers to solve it and all that kind of stuff, which is really, really, really cool. But I also thought it was cool that you could use a bunch of different types of math, like algebra and geometry and symmetry groupings, to solve it. And I just thought that kind of was really neat. So that's basically the gist of it. It's just those sort of 3 examples that I wanted to talk about. Thank you so much for listening. I really appreciate being given the opportunity to talk about this here and sort of read about this problem in convex sets. So I hope you enjoyed. Thank you very much.